Okay, so we're continuing on with sampling distributions, but this time we're looking at the distributions of sample mean. Alright, our goal here is to be able to anticipate the shape, the center, and the spread of a sampling distribution of sample means without having to do a simulation. So we've looked at patterns, and we're going to look at overall how do we know shape, the center, and the spread, which will be helpful for us as we solve some problems later on. So for shape, it can be approximately normal, but it depends on the sample size, and we'll dig deeper into that in a moment. The center is the mean of the dot plot of all the x bars, and it's approximately the same as the population parameter, since x bar is an unbiased estimator of mu. All right, again, remember every dot on this dot plot represents an average from a sample, and the average of our averages should come out to be almost identical to the population parameter. So we can use this right here. The mu of all the x bars is approximately the population mu. So spread. No matter what the shape is, the sigma of x bar, the standard deviation of my x bars, gets smaller as n, my sample size, gets larger. All right, so what are the mean and the standard deviation of the sampling distribution? Well, we kind of hit on this, but here's the formulas. The mean of x bar is mu, the population mean. The standard deviation of my x bar is this formula right here. It's sigma, the population standard deviation, divided by the square root of my sample size. These formulas are on your formula chart. You don't have to memorize them, but they are available. But you just have to know this is what you're going to use when you're dealing with a sampling distribution of sample means. Now, are there conditions that need to be met for these formulas to work? Well, yes. You can only use this if the 10% condition is met. All right? Like we did with proportions, same thing is true with means here. Got to check that 10% condition before these are viable. Now, it's also true no matter what the shape is. Okay, if the shape of the population is skewed, it doesn't matter. These are still true. If it's symmetric, these values still work. Now, here's a tip for you. Notation really, really matters. The symbols, p hat, x bar, p, mu, sigma, mu of p hat, sigma p hat, mu of x bar, and sigma of x bar, they all have specific and different meanings. Either use the notation very correctly or don't use it at all. You can't expect to lose credit if you use incorrect notation. Even if your numbers are right but you use wrong notation, you can lose points. So know your symbols and use your symbols correctly if you're going to use symbols. All right, so be very, very careful. How do I remember this? Well, all the sample stuff have hats on it. Okay, the population stuff are Greek letters without hats. All right, but learn your symbols and you can do this. What is the shape of the sampling distribution of a sample mean when the sample is taken from a normally distributed population? So if the population is normal, what's the distribution of the sample means going to look like? Well, if the population distribution is approximately normal, then the sampling distribution of x bar will be approximately normal also. Basically, it looks like the parent function. If the original was normal, the sampling distribution will be normal also. Does the sample size matter? No. The sample size does not matter in this situation. If the original population was normal, approximately normal, then the sampling distribution will also be approximately normal. So it's important that you read the questions for that information. So here's an example problem. At the Nutty Peanut Company, dry roasted shelled peanuts are placed in jars by machine. The distribution of the weights in the jars is approximately normal with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Without doing any calculations, explain which outcome is more likely: randomly selecting a single jar and finding that the content weighs less than 16 ounces, or randomly selecting 10 jars and finding that the average content weighs less than 16 ounces. So which one's more likely, basically? Well, because averages, as we talked about, are less varied, they're more precise than individual data points, you would expect a sample mean of 10 to be closer on average than the true mean. Okay, one jar could be way off, but if I take 10 jars and average them, they're more precise and probably closer to the right average. So a single jar is more likely to weigh less than 16 ounces. So same question, but here's part B. Find the probability of each event as described above. So the first one is, what's the probability of a single jar weighing less than 16 ounces? So if X is the weight of a randomly selected peanut jar and its contents, it's one jar. We know that from the question that it has a mean of 16.1 and a standard deviation of 0.15, and that it's normally distributed. So I note that. That's my distribution statement. Instead of drawing a picture, I can do this. And the question is, what's the probability that I find one that's less than 16? So I've established it's normal because it told me it's normal. So I can use norm CDF with a lower boundary of negative 1,000, upper boundary of 16, mean, standard deviation given, and I find a probability of 0.2525. Okay, so the next part says, well, what about a sample of 10 jars? Well, now X bar is an average weight of 10 randomly selected jars. It's not just one, it's 10. And X bar, because the population was normal, it also has a distribution that's approximately normal. The average is the same, but notice my standard deviation has changed. It's now 0.15 divided by the square root of my sample size. Right? So that's changed my standard deviation. And I still want to know, what's the probability of getting a sample mean less than 16? So I use the correct notation here. Norm CDF still. Lower bound's the same, upper bound's the same, mu is the same, sigma has changed because I have to incorporate the sample using the appropriate formulas. And I find out that the probability is 0.0175. So as we stated before, which one's more likely to be off? Well, a single jar is more likely to have less than 16 ounces as opposed to an average of 10 jars.